Hello everyone and welcome to this training session on normal probability distributions. In our earlier session we have looked at the discrete probability distributions where we have discussed slightly in detail on binomial distribution and a Poisson distribution. So this normal distribution actually is treated as a part of continuous distribution. We have discussed the difference between discrete and continuous. Discrete is where there are finite set of values or countable number of values, whereas if a random variable takes infinite possible values, that is what we are considering as continuous normal distribution or continuous probability distribution. And normal distribution is one form of continuous probability distribution. So let's see some of the important characteristics of this normal distribution, because what we observe is normal distribution has several applications as far as the statistics is concerned, for either making some conclusions about a data or even for doing some kind of predictions. So because there are lots of applications that depend exclusively on the normality in the data, understanding of the normal distribution becomes the key factor. So in this particular chapter or in this session, let's deal with some of these aspects. What do we call as the standard normal distribution? What are the various applications that could be using this normal distribution? And how do I get into the estimation process using the concept of normal distribution? The heart of the statistical estimating, which is called as the central limit theorem, we'll discuss about that. And how do I convert a binomial distribution into a normal distribution, which means a discrete distribution? How do I approximate it to a continuous normal distribution? And given a particular data, how do I assess the normality in the data? So these are the various topics which we would be looking at as a part of our current session. Let's start getting into it. Whenever we talk about a normal distribution, a few things we need to understand: that it is a continuous, which means there are infinite possible values. These are all the possible values of the random variable on this side as well as on this side. So the random variable can take any of these possible values. So when I am trying to plot the various values on the x-axis and their corresponding frequencies on the y-axis, and I am joining all the points, the shape is coming like a bell shape and it is symmetric, which means when we are drawing a central line, we see that the left hand side of this particular line is a mirror reflection to the right hand side. And in this kind of a distribution, we have discussed earlier that mean should be equal to the median and that should be equal to the mode. One of the important characteristics of normal distribution. So this particular curve has an equation, and that equation happens to be the one which I have highlighted here: e to the power of minus half into x minus mu by sigma whole squared divided by sigma root 2 pi. Now if I see in this entire equation, there are two variables. One is a mu and one is a sigma. Mu is defined as the mean of the normally distributed data, and sigma is called as the standard deviation. So that's where people also use this statement that the normal distribution can be characterized by two variables or by mean and standard deviation of the data. So the parameters of a normal distribution are mean and the standard deviation. All right. Now, before we go into details of the normal distribution, we need to understand one more concept which forms the base for a standard normal distribution, which we would be discussing in the next slide. We need to understand what is called as a uniform distribution. The uniform distribution is some kind of a distribution where all the possible values, so if I can say that the voltage can lie anywhere between 123 and 125, and all possible values are possible with equal probability, with equal chance. That is what we are calling as a uniform distribution. And when I try to plot, which means the possible values are all these are possible values, and each of them is having a probability like this. So if that's the kind of a graph I have, then it represents like a rectangular box. Anywhere between 123 to 125, this is the probability. So what we are saying is, in this kind of a probability distribution, if I am plotting the probabilities for each of the values, what we are seeing is the area under this rectangle exactly comes out to be 1, because you are seeing that this is 0.5, whereas this side it is 2 units. So the area comes out to be 1. So this is one of the important aspects that goes even into a distribution of a normal distribution or a standard normal distribution. The area under the probability density function is equal to 1, right? So let's use that concept further even for other distributions also. Whenever we use the word probability density function or the graph of all the probabilities for different possible values of the random variable, we are calling it as a probability density curve. And some of the generalizations I can make from the probability density curve is the total area under the curve is always equal to 1, and every point will have a height which is either 0 or greater. It cannot be below 0. These are the two things that define our probability density curve or probability density function. So let's see how does a normal distribution function look like. Now if you see, if I am talking about a normal distribution like this, which is a bell shape, if it has a mean of 1 and a standard deviation, mean of 0 and a standard deviation of 1, I call that to be a standard normal distribution. In a normal distribution, I can have any mean and any standard deviation. But if I can transform that distribution so that its mean is 0, we'll see how to transform it slightly later. But if any normal distribution exists whose mean is equal to 0 and standard deviation is equal to 1, we call such kind of a normal distribution as a standard normal distribution. And couple of conclusions that we can make from that standard normal distribution is the area under that standard normal distribution is equal to 1, because any probability density curve, the area underneath it is equal to 1, and every value, the height of corresponding to every value should be either 0 or more. It cannot be below 0, which means it cannot be below this particular line, The point should always be above that particular line itself. Now, the most common thing which people get confused with is with respect to the area and with respect to the standard deviation. Whatever is shown on the x-axis is not the area. They are the standard deviations, because we have said for a normal distribution the standard deviation is equal to 1, which means here it is 1 standard deviation away from the mean, 2 standard deviations away from the mean, or minus 1 standard deviations away from the mean, minus 2 standard deviations away from the mean. So it is not equal to the area. The area under the curve is this aspect. So we have to be very clear on these two things as far as the normal distribution is concerned. The ones that are there on the x-axis, number of standard deviations away from the mean. What are represented on the x-axis, whatever are the numbers are, they denote number of standard deviations away from the mean, and the area inside the curve which is of significance to us is what is the area. So we have to be that sum of all those areas will be equal to 1, but not with the values on the x-axis. So for our practical usages also, when someone uses a term called z-score, we'll talk about it in the next slide. When someone uses the meaning called z-score, it is z standard deviations away from the mean. If I am saying z-score is 1.5, then it's not the area which is 1.5. I'll talk about a point which is lying between 1 and 2 on the x-axis, which is 1.5, and the area is probably the corresponding to this 1.5. What is the area on the left hand side and what is the area on the right hand side? Left hand side plus right hand side area together should be equal to 1. So that is how the areas are determined. So this is what it is. I can think of the areas between any two z scores. So probably if I want, as a simple example, let's say this is minus 2 and this is plus 1. I want to find the area between z equal to minus 2 and z equal to 1. All we are saying is the general area is always from the left hand side. So because the area of the entire probability density curve is equal to 1, I want to find out what is that proportion of the total area that lies between only this much. If I say z greater than 1, I need to find out only this much of area. If I want to say z less than minus 2, I am more interested in finding out only this area. And we all know that that area will definitely be less than 1 because the entire area is equal to 1. So if I have to find out what is that small portion of the area that is definitely less than 1, or it's a proportion of 1, so that is why we can use the area under this standard normal curve as per our requirement as the definition of probability itself. That's one more reason a standard normal curve has lot of advantages, because the area under the standard normal curve, we can very well take it as the probability of the value either lying between those two z scores or less than one of the z scores or greater than one of the z scores. And here we also need to talk about another topic called critical value. What does that say is, let's say I want from this graph what is that particular z value, what is that particular z value that corresponds to this 95% of the area. let's say I want 95% of the area. So probably leaving out 2.5% on the left hand side and leaving out 2.5% on the right hand side. I want to find out what should be the number of standard deviations on the left and the right, so that I will get an area inside the curve exactly equal to 95% of the total area or 90% of the total area, probably from the extreme left, or 90% of the total area from the extreme right. So that particular value which will give me the area underneath the curve equal to my desired area are what are called as critical values. So if I want, just for an example, if I want the 95% area, and by leaving out 2.5% on the left hand side and 2.5% on the right hand side, the typical values are minus 1.96 standard deviations and plus 1.96 standard deviations. That's a standard feature of the normal distribution. If I want 99% area, like leaving out plus 0.5% area on both the sides, then the z value will be 2.58 on the left and minus 2.58 on the right. So we have some standard values. If the distribution is the normal distribution or a standard normal distribution, we can very well say that is the z value corresponding to an area of 99%. So those particular z values which are on the borderline, which will form the area of our requirement of the standard normal curve, are typically called as your critical values. So the decision or a conclusion of a particular characteristic or a parameter can be done by comparing your calculated value with the critical value. We will have a look at that mechanism. So if at all you have a normal distribution which is not standard, which means it is having a mean of mu which is not 0 and some standard deviation sigma, how do you convert it into a standard normal distribution? A standard normal distribution is the one with mean equal to 0 and sigma equal to 1. So if you have to create that kind of an impact, or sometimes people call standard normal distribution directly as a z distribution. So every particular value of the original normal distribution, non-standard normal distribution, you subtract the mean and divide the resulting value by the standard deviation. So every value gets transformed into a standard normal distribution format. So after doing a subtraction of the mean and dividing by the standard deviation, what you would be observing is the mean of the resulting distribution will become 0 and the standard deviation of the resulting distribution is equal to 1. That in that manner a non-standard normal distribution gets converted into a standard normal distribution. And as I said earlier, anytime you should never confuse yourself with between z-scores, which are the x-axis values, and the areas of the normal distribution. Z-score can be even more than 1 also. 1, 2, 3, all are possible. Whereas as far as the area is concerned, the maximum area under that normal distribution or a standard normal distribution is always equal to 1. So whenever we are deciding the critical values, we said critical value will correspond to some particular area. So when I want 90% of the area, I have to be sure which 90% do I require. Is it somewhere in the middle, which means eliminate 5% to the left and 5% to the right, or 90% from the left, which means 10% of the right should be separated, or 90% from the right, which means 10% on the left should be separated. So based on that, the critical values have to be found out. So the areas are never negative, max they could be 0, whereas the z values could still be negative. So don't confuse between z values and the area under the normal distribution curve. Now, using that information, why are we discussing about all this? Now my intention is to estimate some population values. Like, I want to find out what is the average height of an Indian male. Or I want to find out what is the average weight of an Indian. Or some more things relating to what proportion of seats will a particular political party get in the next elections. So I'm making, that is the main purpose of statistics. I should be able to make some kind of a conclusion or do some kind of an estimation about a particular value based on the sample data. So whenever I collect one sample and try to find out the average of that particular sample or variance or standard deviation of that particular sample, or even the proportion of in a particular sample, whatever is the calculation I am doing on a sample, depending on the sample that is chosen. Let's say I want to find out the average height of an Indian male. Now, going to each and every male and finding his height is a typical difficult problem. Because by the time I measure the heights of all the people, new people will come into the picture. So, the alternative is I will take a sample, probably of on a random basis some 1,000 people, find out their heights and use that information to draw some conclusion about the whole population in general. That is what is the purpose of statistics. Now, depending on who are the 1,000 people who are included in the sample, their average height can very well differ. Now, if I take different possible samples of 1,000 and for each sample try to find out its mean or variance and then draw a graph of all the possible sample means or sample variances or sample proportions, that is what we are calling as a sampling distribution. Again, let me repeat the same concept. If at all I want to find out the height of an average height of an Indian male, because I cannot go to each and every person and measure his height, I take a sample of around 1,000 people. Now, I can take various combinations of 1,000 and each combination of 1,000 people can give me a different average. Now, if I take a good proportion of those thousands, different combinations of thousands, and for each combination note down its sample mean or sample standard deviation or sample proportion, and based on that try to identify the probability distribution or frequency distribution of those sample mean or sample variance and these kind of things. Such a kind of probability distribution which I am getting is what is called as the sampling distribution. So it could be represented either in the form of a histogram or in the form of a graph or a probability function. For example, if I want to take the sample distribution of the mean, which means some thousand people, I find out the mean. It came out as 165 centimeters. So I took some other thousand, some other combination of thousand people and measured their height. The average came out to 167. Another sample of 1000 has given me 168.5. Like that, different combinations of 1000 if I take, I get different kinds of heights. Now, if I take a frequency distribution or a probability distribution of all these possibilities, of all these various combinations, then I call the sample distribution of the mean. And what it is saying is most of the values will be in a small region like this. They are targeting the population mean. So I can try to find out the entire population mean. I can try to estimate the entire population mean using these various sample means. And there have been theories which prove that this particular distribution, if I take the distribution of all these sample means, it will tend to be a normal distribution itself. That's one of the more important fact for because of which we have to understand the normal distribution heavily in depth. Same thing, if I take proportions, like I'm surveying, I have taken a sample of 1000 and I am finding out what proportion of these 1000 people have voted for a particular party. So probably let's say I got 40%. Another 1000 on a random basis when I surveyed, let's say I got 40.5%. Another sample of 1000, another combination of 1000 when I did a survey, let's say I got 38.8%. These are the various possibilities that we have got. So the distribution again of all these values, the proportions of each of the different samples is what we are calling as sample distribution of the proportions. And what is also observed is even the sampling distribution of the proportions will also follow a normal distribution. Whereas when I am taking the sample distribution of the variance, the same aspect, for this 1000 find the variance, another 1000 sample find the variance. So whatever are the various variances that you have got, find a probability frequency distribution for that combination of 1000, for each combination of the 1000. Now whatever is the kind of graph we are getting, that we call it as sampling distribution of the variances. And one thing we have to understand here is the sampling distribution of the mean and the proportions, they were showing a normal distribution, whereas the sampling distribution of the variances, it was not showing a normal distribution. It is showing a distribution that is more skewed to the right. So probably the graph of all the possible sample variances, I have got something like this, where you are seeing that the graph is more skewed to the right rather than normal, rather than having a proper bell shape. We'll talk about what that distribution is called slightly later, or just for your understanding, that particular distribution is called as a chi-square distribution, which we'll discuss about it slightly in the next chapter. All right. Now, this particular sampling distribution concept has brought into existence one of the key theorems in the world of statistics called as the central limit theorem. This is probably the heart of the estimation theory, which simply states if the sample size is greater than 30, irrespective of whatever is the distribution we are talking of, irrespective of whatever the shape the data is following, or if the distribution is normal distribution. Two aspects. If the data is following a normal distribution, irrespective of what is the sample size, or if the sample size is at least 30, irrespective of whatever is its distribution, this property holds true. What it says is, whatever the sample means we are taking, in this case we have taken various sample means, 165, 167, 168.5, whatever are the sample means we have taken, and try finding out their distribution. What it says is that particular distribution of the sample means will always be approximated to a normal distribution. So that's one of the key reasons we need to understand the normal distribution. The sample means of any distribution, if I am taking a sample size of at least 30, the sample means of any distribution will be approximated to a normal distribution with a mean equal to the population mean and a standard deviation equal to sigma by root n, where sigma is the population standard deviation. So lots and lots of practical problems in terms of estimations can be resolved using this central limit theorem. It works under these two conditions. One, either the data follows a normal distribution, or even if the data is not normal, if the sample size is greater than 30. In these two cases, whatever the sample means, if you take different samples and for each sample you construct the sample mean, the means of all those sample means will be approximated to the population mean with a standard deviation equal to sigma by root n. And this is what will help us in building the estimation intervals, which we would be looking at in our next part. So whenever we are talking about a sample mean, the z value needs to be taken as x minus mu by sigma by root n, because the standard deviation is sigma by root n, not sigma. Whenever we talk about individual values, we take the z value as x minus mu by sigma. Whenever we talk about the mean of the population, we talk about the z value which is equal to x minus mu by sigma by root n. Of course, when we take up some of the practical things later, we will understand this concept even more with clarity. Now, sometimes a normal distribution, if the data is following a binomial distribution, I can approximate it to a normal distribution if some of the conditions are satisfied. First of all the conditions of the binomial distribution need to be satisfied, which means the data should be a simple random sample. The sample size should be n. The probability of success is p, and the trials are independent. All those things do satisfy, and along with that, if it satisfies such a kind of a requirement, the NP, which is the mean, is at least 5 and NQ is also at least 5. Both NP and NQ are at least 5. Then I can very well approximate a binomial distribution to a normal distribution. And when I am approximating it, I need to find out the mean of the probability normal distribution and the standard deviation of the normal distribution, because I have to first convert it into a standard normal distribution, and then only I can use it either for estimation purpose or for conclusion purposes. So I can very well take the mean of that adjusted normal distribution to be the mean of the binomial distribution itself, which is NP. And similarly, the standard deviation of the adjusted normal distribution can very well be taken as the standard deviation of the binomial distribution, which goes as square root of NPQ, because the variance of the binomial distribution is NPQ. The standard deviation will go as square root of NPQ, so I can very well take square root of NPQ and approximate it as the standard deviation of the transformed normal distribution also. Then, because we are converting a discrete distribution into a continuous distribution, some kind of adjustment is required, and that adjustment is what we are calling as continuity correction. Just because we are approximating a normal distribution from a binomial distribution, we generally do either plus or minus 0.5 to the existing value to convert it from a binomial distribution to a normal distribution. Suppose I have a statement, what is the probability that some value is at least 8? Then the area under the normal curve, let's say somewhere this is 8. At least 8 means 8 and above. So I will try to find out what is this area. But if I am using this 8 based on an approximation of normal distribution, binomial distribution, I will, instead of taking 8, I'll subtract 0.5 and say I'll take it from 7.5. So this is a better area to use rather than above 8. Similarly, when the question says not greater than 8, which means it should not include 8, then I will start from 8.5 and above. Anything when it talks about includes a particular value, I'll start from below of it. If it should not include, then I start with 0.5 above it. Similarly, at most 8, which means if 8 has to be included, 8 or below, and 8 is inclusive, then I'll do it from 8.5 and below, the area under the normal curve corresponding to 8.5 and below. So those are some of the things that we have to do as an approximations or adjustments in case we are using the binomial distribution and approximating it to a normal distribution, which goes as a part of continuity correction scenario. Then if I have some data with me, how do I assess? First of all, is it a normally distributed data or not? First test is look out for a histogram. If I am looking out for a histogram, if that histogram shows a kind of a bell shape, then you can very well say that it is a normal distribution. But if the histogram does not show any signs of a bell shape, widely deviating from a bell shape, you can very well reject that particular data is not forming a normal distribution. The second thing is look at the outliers in the data. We have different mechanisms of finding out the outliers, but one of the most common mechanisms which we have seen is either Q1 minus 1.5 times the interquartile range or Q3 plus 1.5 times interquartile range. If my data value is either below this or above this, I am calling it as an outlier. Now in the particular data, try to identify outliers. If there are many outliers, one or two at the max, you can very well, if one is present or at the max two are present, you can omit them. But if there are more than one or two outliers in the entire data, then you can very well say that it is not a normal kind of a data. So apart from these two, if I am still finding yes, histogram is fine, outliers are fine, now the third kind of a mechanism to use is a normal quantile plot. What we are doing is, take all the possible values of take all the possible data values on the x-axis and their corresponding z values on the y-axis. The actual data values on the x-axis and their corresponding z values. Z values are coming by each data value, subtract the mean and divide it by the standard deviation. Take their z values. And if you see that the graph between these two is almost a straight line kind of a pattern like this, probably slightly more than this or slightly less than this, but it is a straight line pattern to a large extent, and no other shape is coming out, no other sequential pattern kind of thing is coming out in the graph, then we can very well say that it is a normal graph. But if it is very much away from a straight line pattern, or it is showing some other known predefined pattern, then we are calling it as a non-normal kind of a distribution. Then we are calling it as a non-normal kind of a distribution. Look at these values. There are three types of normal quantile plots I am seeing here. Here if you see, all the points are very much close to this red straight line. Very slightly deviating here and there, and I am not able to observe any kind of patterns in the data. So I may very well say that this kind of data is still following a normal distribution. Whereas here if we are seeing, almost every points are very close to that straight line. Very much close to a straight line, but I am observing some kind of a pattern like this. So if the data, the deviation from the straight line is following some kind of a pattern. If it is following some kind of a pattern, then I can very well say that it is not normal. If the deviations exist, but the deviations, if they don't follow any kind of a pattern like in this graph, we can still conclude that it is normal. But if the deviations are following some kind of a pattern, some kind of a predefined shape or a structure, then I can very well conclude that this data is not normal. One more way to decide this, actually this kind of shape actually will correspond to a uniform distribution. We'll talk about these things whenever required. And if we are talking of this kind of stuff, where a good number of values are above the line and only one or two values are below the line, and they are nowhere closer to this line, then we can very well say that this is not normal. This will show a kind of a skewness to the graph. And because majority of the values are above the line, we can also conclude that it is positively skewed. So this kind of analysis can decently be done with respect to our normal quantile plot. So just a simple, there are a lot of tools which can help us in plotting this normal quantile plot. They can help us in determining the normality in a particular data. But even a simple histogram can help us, or even the understanding of the outliers also can help us in assessing the normality of the data. In case the data is not normal, it is very much advised that you convert it into normal, because lots and lots of statistical analysis, including the estimations of various parameters, will depend on the basic assumption that the data is normal. We will be seeing in our upcoming chapters also that if the data is not normal, I cannot apply so many conclusions, I cannot perform so many conclusions or so many estimations or different predictions on that particular data. So it's always advised that I transform that particular data using some kind of functions to make it normal. The most common transformations which people do is either a log transform, or a square root transform, or a reciprocal transform, or a square transform, which means each value of the original data, you you make it as log x plus 1. Log x plus 1. If you see that the values are following a normal distribution after making it log x plus 1. So probably if you have a value 3, then you make it as log 4. Or if you have the value as 7, make it as log 8. So after you take all these values, try seeing if this data is following normal distribution. Again, either using your histogram or outlier check or even the normal quantile plot, any of those mechanisms, check out if the data is following a normal distribution after it is transformed by this. If it is not, then follow these kind of transformations. Try root x, which means every original value of x, find a square root of that, and then try out this process, or do the reciprocal of each of the values and try doing the and try looking at the transformation, and try looking at the distribution, or do the square of the original values and then look at the distribution. If in any of these cases it is following a normal distribution, our further work will be on this kind of transformed values but not on the original data values. That is one more thing. In case we are observing a particular data to be not normal, I should be able to convert it into normal by following the transformation process. And if I am doing it by taking logarithms, the original data is set to follow what is called as the log normal distribution. If by taking the logarithm of each of the values, I am able to make the distribution as normal, what it says is we can very well conclude that the original data is following a log normal kind of a distribution. If you have any further questions regarding this chapter, you can feel free to call me on 98480 or you can send me an email on vamsidhar@pacegurus.com. I suggest you visit our website www.pacegurus.com for further updates regarding the various training and consulting programs we do in the area of finance, analytics, statistics, and investments, using the tools like Excel, VBA, and SPSS. I hope this session gave you a full detailed understanding of the normal distributions. Thanks a lot for listening to this session. Thank you very much.